Good morning, gentlemen. Today we will continue to some extent the topic which we took last time. That was about quantum corrections. What is quantum correction? In fact, it is a consequence of interference. We have a wave which is delocalized in a complex media with lots of scattering. So there is interference between a wave which goes through and scattered waves. To get it ultimate, these waves incoming and outgoing can be of the same amplitude. This is a signature of localization. So ultimately, we go to a kind of box, localized state, where we have a standing wave, which is made from two waves of the same amplitude. So that brings us to quantum dots. We will define first quantum dots. It is something which requires definition. A very practical one. Most important signature of quantum dot is a visible quantization of electron spectrum. So we will look at discrete levels into geometries, simple geometries, box and ring dots. We will talk about persistent currents in this dot, circular currents which you can induce by magnetic field. From the levels, we go to states, quantum states of the dots. It has to distinguish between these two because there's interaction in the dots. Mainly, it's something which we know, it's Coulomb blockade interaction. That sets a transport problem, which we address in the dot. And we will talk about transport for a while. Then I'd like to change the topic. That will be in the second half of the lecture, and come back a little bit to random matrix theory, which we have shortly discussed last time. And random matrix theory allows us to understand what is chaotic motion at quantum level and give some predictions about levels in chaotic system. And we will talk again about level, repulsion, and different ensembles a little bit at different angles. Fine, so this is a program for today. Quantum dot. Let me start with a definition, which might be a bit boring, but practical. What is a quantum dot? A quantum dot is a place where particles, usually electrons, are confined in visibly discrete levels. Why it has to be visible? Why? It is a part of the definition. Let us take Eiffel Tower, which is made from highly conducting metal. Let us lift it and isolate from the Earth. In principle, electrons in Eiffel Tower will be isolated, and since they're quantum particles, they will form discrete spectrum. However, the volume of the tower is that large that the level differences mean difference between the levels will be astonishingly small. Nobody would see that. It is also difficult to see even in metallic islands of submicron size. It's a matter of instrumentation, but in these islands where quantization again, this mean distance between the levels is of the order of microelectron volt. It is still difficult to resolve the spectrum. Right. So practical value at the moment is something like 100 microelectron volts, and kind of many dots, which are artificially made structures, have a level spacing of this order. An atom actually also satisfies the definition of quantum dot. Their level spacing is of the order of 10 electron volts, much bigger. But okay, we are not about atomic physics. We still cannot have a difficulty to take a single metal and put electrodes, study transport through a single metal. Although people nowadays do it with single ions in silicon substrate. That brings us to the scale of like 10 nanometers, something like that, 5 nanometers. And quantization, spectrum quantization, like, let's see, what was that? Like 100 millivolts. But still, it is rather far from atom. Good. So let us make some classification of quantum dots. Roughly, they are, just by virtue of preparation, virtue of fabrication, can be made into two classes. The dots without metallic leads, conducting leads, and those with leads. So in this case, you can see how electrons will pass through these dots. Here, it looks like you cannot assess this, but what you could do is to do optics. All right, so there are examples of the dots. Could you tell me which dots are optical and which dots are transport? Yeah, how did you come to this conclusion? Okay. Fine. Good. You're right. Well, these dots don't have visible anything which you could regard as leads. Both dots are made in semiconducting heterostructures. It's very flexible I couldn't say material, perhaps a material, two-dimensional material. These, since we are in quantum transport, let me try to zoom in the picture. Perhaps it doesn't crash. Sometimes it does, but hopefully not today. Oh, my picture appeared. Fine. It is something which is made on a semiconductor nanostructure with two-dimensional gas. So all this black would be two-dimensional gas. To shape it, to make eventual structuring, they put from above metallic electrodes, a whole series of that. They don't have electric contact to the 2D gas. But they, if you apply voltage on these gates, you could deplete two-dimensional gas. And let me figure out what is eventual shape after depletion. All right. So you can contact to these areas, and also from this side, supposed to be independent contacts. Mm-hmm. And the dots, it's a double dot system. The dots are eventually here. Good. So electrons may go like this. The advantage of this funny system is as follows. Here we also have something like junction, something like point contact. Quantum point contact does have to be ideal. And if there is a charge in the dot, it will change something in the contact. Will repel electrons also there. So the resistance of this contact will change, which can be measured. So this device not only measures transport through the dot, it has an ability to measure the charges of the dots. Right, that's perhaps this scheme is so popular, so you have seen it in many pictures. Now I want to zoom out. Good, I'm almost done. Let me mention again, conductance quantum comes in every lecture on quantum transport, irrespective of the topic. And let me mention that in order to have good level quantization, the conductance of the junction between the dot and the leads must be much smaller than conductance quantum. So we are somehow in tunneling regime. To confuse you a bit, sometimes people talk about quantum dots, eventually assuming geometry like this. So there is some place where you can store electrons. This is good. That's why they call it a dot. But the contacts are eventually pretty much transparent. So there are no localized electron states in the setup. And these quantum dots do not fit our definition. But sometimes you can find such ideas in the literature. Good. Quantum dots, as I said, the spectrum must be quantized. Let us see how does it work. Let us take something simple. Let me take, okay, I'm in two-dimensional gas. It's simple two-dimensional geometry. Of course, there are also three-dimensional dots. But let us talk about two dimensions. Let us assume that we manage to make potential gates such that there are hard whirls in both directions. Right? So wave function must be 0 at all four walls. Then what we have to do for the spectrum is just recall our story about waveguides, lecture number 1, and understand what are standing waves which fit the dot, which fit this geometry. And the energy of the levels, which is kinetic, we don't assume any potential at the bottom, will be given by discrete wave vectors in x direction and y direction. So that will give us a spectrum, some constant, and these numbers. Right here, I plot the spectrum. I believe I've taken a little bit different dimensions in vertical and horizontal directions to remove degeneracy of the dot, which I would encounter in this case. What we can see, it's good to plot the dot, the spectrum as a series. So if for each series I fixed an I, and I plotted for different nx, increasing in this direction. So you see that in each series, higher levels come with bigger and bigger spacing, but simultaneously other series start there. So in average, in two-dimensional situation, average space in between the levels does not depend on energy. That's pretty convenient. Right, here there is an estimation for this, I have few numbers, but sometimes I give them. It's level spacing in gallium arsenide heterostructure where effective mass is small, which is good for big level spacing. So this is level spacing in units of electron volts per nanometer. So if the dot would have been nanometer size. The spacing would be like 4 electron volts. That's too much, so, but it's 100 nanometer. It becomes reasonable quantity, 10 to the minus 4. So we can see these levels clearly. Fine, those are levels in the box. I will mention in the end of the lecture that box is eventually very special geometry, separable geometry with no chaos. But let's postpone stress in this circumstance. Good. No questions? Let us consider one simpler situation. Let's imagine that we can make a quantum dot in the shape of the ring. So in this figure, white is a place for electrons, which again confined by impenetrable walls. And let me assume that this area is sufficiently thin, so there is a quantization in radial direction, and I pick up only the ground state. Good. Then, surprisingly enough, I find myself in one-dimensional situation. So, electron just goes around the ring, and the angle phi is a good coordinate to characterize its position. Let us see, what can I do? I can sketch the Hamiltonian. I will put magnetic field because it's fun to do it with magnetic field in this situation. Right. Now I want to make it one-dimensional, so I will express momentum, which is derivative with respect to coordinate, as a derivative with respect to phase, and a vector potential I'll express in terms of the flux in this area. Okay, here we are, the Hamiltonian. So it is a derivative in phase elongated with the flux. Right, it is pretty easy to find eigenstates of this Hamiltonian. Those are just plane waves, periodic functions. And look, I have to make this wave vector discrete to assure periodicity of these wave functions with a period 2 pi. Fine. After that, I got the energy. And we currently here not a physical but theoretical physics analogy. If you remember the story about Columblicate, we have had very similar expression of shifted parabolas. So we have discrete variable which labels as parabolas and continuous variable which tries to make certain discrete value energetically favorable. All right. So if I change flux, I will have periodic picture. It's not surprising because it's a Rotherham effect, but that n would increase with increasing flux. Good. Now it's a quantum question, not for this course, but for your standard quantum mechanical course. This discrete number. It's called. There are multiple names for this. All right. And you encounter this when you talk about angular momentum. I hope it is still a topic in your elementary course of quantum mechanics, or is it not? Eh? Let's go step by step. Did you take the quantum mechanics? Fine. Did you hear about atoms? You know, this spherical things? Fine. Did you look how spherical symmetry is manifested in quantum mechanics? Mix it. So for spherical symmetry, we have angular momentum quantization, which gives you different orbitals in atoms S, P, F, D, and so on. Here we have only one rotation axis, but that's fine. We can define projection of angular momentum onto this axis. And kind of a big issue in quantum mechanics is that this momentum is quantized. Angular momentum is quantized. That's the quantization which we encounter here. So in fact, well, it's logical. We apply a magnetic field. We try to make electrons rotating. That's why angular momentum increases, but it does it in discrete fashion. Good. That is ring-shaped quantum dot. And we see that the levels depend on flux. Let me talk a little bit. It used to be an important topic in quantum dot physics. Right. First of all, let me understand that there can be currents in the dots. Well, it's not the currents we can readily measure with ohm meter, voltmeter, whatever, right? Because there is no leads in the dot. Nevertheless, if you have a dot, doesn't have to be spherical shape. If you apply a magnetic field, there is some circular current going on, even in the ground state of the dot. So there is a relation between this current and energy of the dot. So this relation is very similar to Josephson relation we look for, but for this circular current. The derivative of energy with respect to flux just gives you the current. Very good. So let us look at the dot under consideration. We can fill it with many electrons, and we can have the dependence of levels on flux. Let me see what kind of curves will we have? Right, so I guess that is for 1, 2, 3 electrons. So we see that these curves are made from linear functions, linear segments. Well, that's because we have parabolic segments here and here. We also see, perhaps it's convenient to see in this picture, that this persistent current does not increase if you increase the number of electrons. Why is it so? Derivatives from, if you fill these levels, derivatives always come with alternating sign. Plus, minus, plus, minus, plus, minus. So it doesn't grow. It just oscillates. Good. And it's periodic in flux. Right. So there are many experiments to equilibrate this dependence to measure such persistent currents. It's been challenging experiment. That's why it was so popular. Again, these currents cannot be measured with ohmmeter. How would you measure them? How do you measure current if you cannot have contacts? Yes, 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 yes. This is more or less only way to measure the current. So, in fact, they cannot, they measure magnetic response of the dot. Apply magnetic field, measure magnetic response. Well, it's difficult to do it for a single dot, if ever possible. There is a chance if you make lots of quantum dots of approximately the same size. And there's also magnetic response from the substrate, from all details of your refrigerator. So let us see, are we in trouble? How to separate the response from the dots and the response from all other parts of your apparatus. You apply magnetic field, usually it's a coil like this, right? So it's magnetic response from your sample holder, from the walls of your fridge, magnetic response from all parts. And there are tiny dots put somewhere. Come on, guys, some ideas. Let's brainstorm this. The answer is clearly given at this slide. It is so there is a magnetic response, magnetization as a function of magnetic field. There can be some regular dependence, but one would look at periodic part of the signal. It's difficult to make the dots of exactly the same size, but you can try to do your best. So there is some period related to this. Good. Persistent currents in the dots. Let me now get a bit more practical and let me talk about the levels, which are placeholders to put electrons, and actual dots where these levels are filled. And certain filling of the levels, if you forget about interaction, just brings us to a certain quantum state of the dot. Right, so I just took an example of the dots with 6 spin-degenerate levels. And I put certain number of electrons. I could put 8, but I decided for 6. That's a ground state. That's a ground state. So green levels are filled. Now I want to look at other states. And it's convenient to me to talk about electrons and holes. Say holes is the absence of an electron at green level. And yeah, I could put electron to an empty level as well. Right. So the total number of electrons is the same. It's fixed. And all excited states I can see as creation of some number of electron hole pairs. Because number of electrons, number of holes should compensate each other. Fine. Let's see what's going on. It's rather instructive picture, which you can get. That are states of the first generation. Then one can create more electron hole pairs and position electron hole pairs everywhere. That's the second generation, third generation, and so on. Let me plot energies of what I get. Those are levels. I've taken a little bit more levels than for them earlier. How many of them? I guess 10 or 12. And right, I just plot the energies of the first generation, second generation, and so on. Right, all there's some minimal energy per generation which grows. So that's where first generation starts. Here we have the second. Here we have the third. And the level spacing within a generation first is rather big, then becomes smaller and smaller, smaller and smaller. And then we have usual game of big numbers. Yeah, I guess everybody knows this story about invention of chess. Do you know the story about powers of two? Okay, who knows the story about powers of two? You don't. Good. So it was a story about a Shah who has ordered to invent interesting game for his leisure, and those inventor of the chess brought the chess. They played. Shah was really impressed. He said, "Well, Just ask me whatever you want. And he responded very greedy. So you see, there's a chess desk, and let's put 1 grain onto the first cell, 2 grains onto the second cell. Okay, I got it. Said Shah. I will give you that so much grain. But then, kind of clever people explained, Shah, that despite the fact that chess desk looks small, 2 to the power 64 is much more grain that has been ever grown by people. So he had to kill the inventor. Fine, something like that we encounter here. So if we take energy strip, which houses a reasonable number of levels, say 10, and if you want to count number of states, it appears to be exponentially scaling with this number. So here took 10 or 12 levels, so it goes from 0 to 10, but already in this strip, I have more than 2,000 states. And if I increase the level spacing, if I increase this energy strip, I will have yet exponentially more levels. So one has to be careful with exponents. What is the consequence of this? Also, it's something which is clearly seen experimentally. By democracy principle, we don't see the levels, rather we see the states. So, in fact, even if the level distance, average level distance is large, we have to resolve the states. And if we go to excited states, the level spacing will become small very, very quickly, right? Which means that we can see discrete states and quantum dots only at sufficiently low energies. Well, somewhere here we will have already a difficulty. Good. Levels, states, number of states increases exponentially with energy. Right. That was without interaction. Let me talk a bit about the role of interaction. Eventually, there are different interactions, and most of them don't do much. Right. We have the states with different number of electron pairs. What interaction does, it arranges it so that actual states are linear superpositions of these non-interacting states. Right. It is important that interaction splits the states with respect to spin exchange interaction. Let me illustrate it with these 4 states, eventually first excited states in the dot which I have. I intentionally do not put spin in first picture. Let me put it now. So in fact, understand I have 4 states corresponding to different direction, to possible directions of electron and whole spin. Right. So what does the common wisdom tells me? From these 4 states, you can make a state with 0 total spin, which is single state. Or you can make 3 states, degenerate states, with spin 1. Spin 1 has 3 projections, -1, 0, +1. And if you don't apply a magnetic field or something like that, these 3 states will be on the same level degeneracy with respect to spin. And what interaction does, it provides energy gap between these states. Right. There is spin orbit interaction, which actually splits the states of high spin. But I already have to mention the most important interaction in quantum dot physics. And this is something which you know. This is charging energy, Coulomb blockade interaction. Good. So I'd like to have the same system which we'll look at for Coulomb blockade. Right, and instead of an island, metallic island, without visible quantization of spectrum, I just put quantum dot. What will I see? Well, eventually almost the same. There will be charge and energy set by capacitances. This capacitance can depend on n eventually, but usually it's rather smaller. Right, so we'll be charging energy and the number of electrons in the dot. One can manipulate with this gate electrode. The only peculiarity that one cannot really make holes in the dot. So one can only add electrons in there. So there will be one-sided ladder of discrete charge as a function of gate voltage. The dot can be emptied. For all dots, I know Coulomb energy still dominates on quantization energy. You remember that for metallic islands, it's a 4 orders of magnitude. For quantum dots, it's a factor of 2, factor of 10, but Coulomb energy is is bigger than the quantization of discrete levels in the dots. So it still dominates the transport properties of the dots. Good. I have to go to transport, but perhaps it's time for a break. Let's have 6 minutes break. Do I have to stop video? Coulomb blockade, still most important interaction. So let us see what we have for transport. Let me first outline general situation before going to concrete examples. Let us see what has changed with respect to the situation with Coulomb Islands when we neglect level quantization. One has to care about not only about total number of electrons, but also about concrete state of the dot in the configuration with given n, which makes it a bit complex than for Coulomb blockade circuits. Transport is characterized by probability distribution to be in all the states. Right, so there are rates of various processes in the dot. There are single electron processes, single electron transfers. Again, we assume there's like a set transistor configuration. There is a left junction for the dot, there is a right junction. They go through. So there are rates which, well, they increase or decrease n by one. One electron is transferred. And simultaneously, they could change the state of the dot. In addition to this, there are rates which do not change the number of electrons. How come? Suppose the dot is in excited state with an electron-hole pair. This electron-hole pair can collapse, can annihilate, disposing energy somewhere. Okay, so there is a relaxation transition. N stays the same, S has to change. Good, and if you know the rates, all the relevant rates, we just plug in into master equation. It should work. So in homework, there are several examples about transporting quantum dot. I thought I have a transparency about the rates. Oh yeah, okay, it will come further. Okay, let me first talk about single electron tunneling. Right. Again, energy consideration applies. Energy difference between charging energy and which includes also voltage of the leads. They have to be negative for rate to be non-zero for process not to happen. In distinction from complicate, these rates for a single level, hardly depend on energy. So if it is allowed, then it takes some value gamma, not depending on energy. There's a transition between continuum of electrons in the lead to an empty level in the dot. Right. Let us figure out the relation between this rate and conductance of the junction between the dot and the lead. We have looked already at this formula very shortly last time, I believe. But anyway, not, simple things it never hurts to repeat. Let us consider a situation where not a single level is available for tunneling, but rather many levels are available. So I put a Fermi level somewhere here. Good. Then how can I estimate the current? The current is proportional to number of levels available for tunneling. Tunneling rate for a single level. Yeah. And electric charge. What is the number of levels? It is a width of energy strip in units of quantization energy. Fine. So I got the current, which is proportional to voltage, but this is definition of the conductance. From what derived, I see that the rate, tunneling rate, is quantization energy times a factor, which is a conductance in dimensions units. That actually proves what I told you in the beginning of this lecture. Small conductances are required for discrete levels. Indeed, let us have a discrete level owing to tunneling. This rate, this level will become kind of smoothed. There will be energy uncertainty, which is precisely this gamma. Right. So if this gamma is comparable with the distance between the levels, the effect of quantization is gone. So the conductance must be small. Fine, good. We figure out the rates. It was single electron rates, relaxation rates. I don't want to talk much about those because if I start talking, it will be very, very, very long lecture. Many mechanisms are responsible for relaxation rates in quantum dots, and the rates, actual rates, vary depending on circumstances in a very large window. Let me just mention most important issues with that. If I have an excited state in the dot, like electron-hole pair, it would like to relax and annihilate. But it has to dump energy somewhere, right? That's why some environment is needed for relaxation. It could be phonons, because the dots are in crystal lattice and not having vacuum. There are always interaction with vibrations. It could be photons, excitations of electromagnetic environment, quantum dot field. And in this case, it just becomes quantum, which flies away somewhere. Interesting process which can occur is a conversion of electron-hole pair in the dot to electron-hole pair in the leads. So in this case, quantum dot is back to ground state. Funny enough, it can occur without tunneling through the barrier. Of course, each component one could tunnel, to the lead, but it doesn't have to, because this process does not involve any charge transfer. Charge transfer is zero. So no particle has to tunnel, just electron interaction between electrons in the dot and in the lead would do the thing. All right, that's what I wanted to say about relaxation rates. Let me concentrate on a very simple, very generic situation in quantum dot transport. I will consider similar to Coulomb plane of bias voltage and gate voltage. And I set bias voltage to some small value, smaller than level spacing in the dots. Right. That sets me energy window, and I can tune with gate voltage the system of the levels in the dot. And I tune it in such a way that an electron is there in this energy strip. Just single level is there in this energy strip. Fine. What will I get then? If this voltage applied is zero, very narrow strip, then I could achieve this only in a point of gate voltage. Well, if it's not zero, I will achieve it in some interval of gate voltage, right? So in general, I have, well, I could call it a cone if you don't protest. And within this cone, with this region, I have a current going through the dot. Right. How much current? Oh, that's rather simple to figure out. I believe we did it at homework, something very similar, which I explained on Tuesday. So we have stochastic electron transfer through the left junction, right junction. We can determine probability for the dot to be either in state with an empty or field level. And from that, we can figure out the current. Here's the current. Right. The rates don't depend on energy, which means that the current is constant, either zero or constant. That's interesting because it looks that there is a sharp step of the current. What can smooth this sharp step? It could be temperature. And in this case, this other step in energy is given by temperature. What would be maximum conductance? Sorry, I forgot to say that. Sharp step, if it were really sharp, would imply infinite differential conductance just in the point of the jump, right? You differentiate jump, got delta function, infinity. Okay, if you smooth it, there is a finite maximum conductance. which would look like this, inversely proportional to temperature. So that's a signature. One could measure conductances and see that they increase with temperature to start with. But suppose temperature is 0. Would it imply that the step is sharp? No, it does not, because, as we just discussed, there is some intrinsic level width given by the rate. Right. If we substitute it to our estimation of conductance, current divided by this width, we will come to the values of the order of GQ. That's a bit funny, but we understand that's pretty generic situation. Conductance of the dot of each junction is much smaller than conductance quantum. However, if we take the dot and bias it to the edge of this region, we have conductance which is much bigger of the order of GQ. We have seen this situation once when we talk about two double barriers and transmission through the double barrier. We have found that sometimes if the barriers, if the transmissions of the barriers are very low, there's still a chance to get transmission of the order of 1 of conductance quantum. There was a resonance. So sometimes this is called resonant tunneling regime to stress the analogy with this. Right. The problem is simple if these levels are split in speed. It becomes much more complex and even unsolvable if the levels are degenerate, so it has two spin components. In this case, interaction effects take place, but fortunately, they modify the picture only quantitatively. The same estimations are still valid for the Jeanette level. Right. Am I done with transport? Oh, okay. It's also useful for homework. Let me just shortly mention what will happen if I take excited states in the dot. So if the bias voltage is low, then, okay, here the resonant tunnel regime. We talked about this. In this case, the transitions are between ground states of the dot with different number of electrons. Suppose I have excited states, and at this, for this example, what did I do? All right, I have two ground states for different number of electrons and excited state in each dot. And even with a simple small addition, I will have much more complex picture of the transport. Right. So now I can tunnel not only between A and B, starting from some energy. I can, for instance, tunnel between A prime and B, A prime, B prime, and so on. If I apply sufficiently big voltage, I would tunnel between the states. So I have a series of different regimes. Well, how many do I have? Looks like 5 if I exclude trivial regimes of Coulomb blockade. Right. So I have different transport regimes in all these regions. I can find energy considerations from if I just compare energies of the states, understand how much energy do I have to pay, draw the cones corresponding to each tunneling. That would be that's how can I can distinguish different transport regimes. There's a large exercise, large problem in your homework about this. Very good. I don't frequently show you experimental pictures, but here I would show one. It's Coulomb diamonds in a quantum dot setup. Quantum dots, again, it's also an example of universality in quantum transport. You observe it in many systems. We've been talking about quantum dots in two-dimensional gas. This is a quantum dot made in a carbon nanotube placed between two electrons. Carbon nanotubes have a pretty small diameter, like 5 nanometers, I guess, something like that. But they're pretty long. That's how carbon grows. They managed to catch one, put it between the electrodes. Due to electrostatic repulsion, there are barriers formed here. There are some electrons in the nanotube. So it becomes yet another realization of quantum dot. So what do we see here? First, the color shows us differential conductance. So here it's about 0 in this Coulomb diamonds corresponding to different ends. The conductance increases, there's current going on, and what you can see here are discrete lines. Each discrete line gives you an excited state, a level in the dots. You analyze it and you see that more and more excited states come into play. So in fact, somewhere here, you don't see much of discreteness. It already becomes smooth. As I explained, you owe into a big number of states which are available for excitation. Right. That was in illustration. Let's see how much time do I have. About 20 minutes. So that should make it for chaos and random matrix theory with respect to quantum dots. What we can see from the picture that the levels are in principle experimentally observable. Not so many of them, but well, one can count 1, 2, 3, 4, 5, 6, 7, well, perhaps 8, 9, 10 levels, let's say. And one could think of different problem. One could think of the energies of the levels in quantum dots, just in general. To start this discussion, I first have to get to classical mechanics. completely classical mechanics. There are electrons, particles, which are in confined geometries. So once you shoot such an electron, it would forever circulate in the shape of a certain, in a cavity of a certain shape. Right. Let us understand now the difference between ordered geometries, separal geometries, and most general one, common geometries, which lead to chaos. I wonder if somebody told you about this, could be in course of mechanics or some other course when people talk about chaos. In my time, not in my time, the generation after me, students were very chaotic and they've been interested in chaos and understanding the basics of chaos very much. Used to be a popular topic, perhaps not for your generation, but still let us recognize very simple and interesting facts. I took a box. I sketch an electron trajectory. And I see now that it's pretty regular. It repeats itself many times. Let me try something different. Let me try a cylindrical quantum dot. I start with a trajectory and I see it repeating in a different fashion than that, but still the trajectory is very regular. And if I look at it, I see, for instance, that the particle never enters this area of the dot, which is obvious for this trajectory. It does not sweep the whole area of the dot. Right. This is because, like in our example waveguide, two-dimensional motion can be separated into independent motions. In that case, with respect to x and y, in this case, in radial and angular direction. So that's example of separate geometries. Why do we ever look at this, I would say, degenerate cases? That's because they're easy to solve, easy to understand. That's why I talk about this in the beginning of the lecture. What is a common geometry? Mathematicians like 50 years ago began to play billiard. They decided to look upon, let us just change a bit the spherical geometry. Let's add a rectangular section in addition to two spheres. And let's us look at electron trajectory. And it turns out that even if the section is very small, it changes the characteristics of electron motion qualitatively. As you see, the trajectory here covers the whole billiard, becomes very democratic. And it's completely disordered and predictable if you find an electron here after several collisions with the walls. It will have absolutely different velocity, and you can't really predict it. So this is what is called chaos in classical motion. And I would stress it again, this is common. If geometry deviates even slightly from separable geometries, chaos sets up, and simultaneously, too bad for our brains, we lose our ability to predict these trajectories, to express them mathematically. Okay, that's reality. Now, how about quantum? So let us take a system which in classical approximation has this chaotic stability, chaotic property. And let's see how the spectrum is quantized. Again, I told you, I guess, a story of Wigner and Dyson, who's been confined in some highly classified area to work at the nuclear physics project. And they've been extremely bored, and they wanted to make something creative. So they decided to make quantum mechanics of completely random system, which appeared to fit nuclear data pretty good. So they proposed statistics for energy levels in disordered system, which is called Wigner-Dyson statistics. Let me compare the spectrum in separable geometry with Wigner-Dyson. Which is in separable geometry, the spectrum consists of series. That, say, hydrogen atom is also an example of separable geometry. And the levels in different series do not have any problem to come very close to each other. I had an example, I guess, in here. Right. For instance, here, they come very close to each other. That's too much. In distinction from that, Wigner-Dyson distribution has a property called level repulsion. The levels avoid each other, never become degenerate. As extreme, if one takes completely independent states. Well, suppose I have different isolated quantum dots and I take all possible levels from there, then I will have Poissonian distribution of the levels, and also in this case there is a chance that two levels come close to each other because they just belong to different dots, for instance. It's also, this Poisson statistic is in sharp contrast with Wigner-Dyson distribution. Okay, you might say that there's order in each chaos, that chaos, how to express it, at the level of common wisdom, at the level of our language, chaos in an order are frequently opposite. But in fact, we see that chaotic systems are much more ordered than, say, random systems. So in fact, there's order in each physical realization of chaos. Let's see, random matrices. Each quantum system can be described by Hamiltonian. Each Hamiltonian is a matrix. simplest matrix to analyze is a random matrix. That's what Wigner Dyson assumed. So there's a matrix, and the elements of this matrix are zero on average, but same elements, same is expressed by this delta function. They have some finite variation, they're independent. Right, so in total distribution of the elements assumes a linear normal distribution, Gaussian distribution. Let us see how levels are distributed. So there's opposition between elements of the matrix and levels, which you get as a final product of lengthy diagonalization of the matrix, which eventually takes all the elements. To understand repulsion, let us look at the matrices which we can easily diagonalize with just two by two matrices. Right, so let's distinguish two types of matrices. This matrix is symmetric. And if your system, quantum system, has time reversibility, you can express it with the help of symmetric Hamiltonian, completely real Hamiltonian, because it's a Hermitian. Right, so that's what they call orthogonal ensemble of matrices. So what is the Hamiltonian? That's only Hamiltonian one can write for 2 by 2 matrix. This H is irrelevant. It does not change the level splitting, just shifts both levels by the same amount. The splitting is like this. And if these quantities are uniformly distributed, the probability to have a certain S scales like S. Why is it true? Oh, this is just transition to polar coordinates. S is like a radius, so we have integration over dHz, dHx, and we are interested in integration over the radius only, so it becomes S ds. Here it is, level of repulsion. Let's take a different ensemble where all matrices are allowed. And there are 3 independent elements. And consequently, the repulsion, this integration transformation will give us S to the squared. Stronger level repulsion. Good, that's what they figured out instantly. The merit is to extend it to the matrices of big dimension, actually infinite dimension. What they figured out, that's the Wigner-Dyson distribution of all levels. Levels never come to each other, right? These vectors forbid degeneracy for each pair of levels. It is characterized by some power. This power is different for different ensembles. Good, so this is level repulsion, and there are terms which confine levels. If, you have intuition for that, if the levels repel each other, they would go away. To keep the levels in a certain window, one has to apply this term, this confining potential. Uh, Electrostatic analogy, I guess I shortly mentioned this. If one considers the levels as a position of particles, which are in a one-dimensional space on an axis. Right. The statistics is the same as these particles are subject to logarithmic interaction, and there's some external confinement potentials. And they experience thermal fluctuations, so, okay, they still fluctuate with the temperature. And this temperature, as we discussed, takes 3 discrete possible values. Right, so it is analogy of Boltzmann distribution. Right, it gives us necessary intuition. So the levels never come to each other because of repulsion. They're still confined, they don't fly away, or into confining potential. Good. So what is important for us? What is the main message of this order coming in chaos? It's best expressed in terms of number of levels in some energy strip. Okay, the system is still random, changing, say, implying magnetic field to the dot, so taking another dot, we have different realization of the levels. We can talk about variation of number of the levels. Right. So if the levels are random, if the levels are taken from different dots, from independent systems, the variation, as you know, perhaps from your first days at university, the variation is proportional to n, right? So the accuracy of measurement, relative accuracy of your measurement is 1 over square root of n, right? This is the same formula. Random levels. Wigner-Dyson statistics predicts much smaller values. It is called spectral rigidity. So there's for sharp strips and there's some log dependence and there's temperature coming. If the strip is a bit smooth, logarithmic dependence is gone. So variation is of the order of 1. The levels in chaotic systems appears to be much more ordered in this sense. I usually tell a short story to stress qualitative difference between these two regimes. So let us see. We are in the city or town. I would call it town. I don't know how about you guys. Do you see Delft as a city? Anyway, it has 10 to the 5 inhabitants. Let's estimate the fluctuation of number of inhabitants by random statistics. So we have square root of 10 to the 5. It would be about 300 people. And it's kind of, you don't feel any protest feelings against this. People come and go, they go to other cities, they just go outside of the city. So no problem. It looks like some people come, some people go away. It looks reasonable estimation for the fluctuation. Now, suppose you're given a task to make sure that this fluctuation about 1. So how to achieve it practically? Perhaps you're more creative. The only way I see is to put barbed wire wall across the city perimeter and put German herders to patrol the wall and to have only one door in this wall. This is constantly checked. But that will be a qualitatively different society from what we used to live. That stresses qualitative difference between the regimes. Very good. I think I'm done for today. Thank you for your attention. Important, I will also write an announcement about this. Next week, I will be available only in Zoom. I will be abroad and won't be able to give lecture in this room.